Okay, now we're going to do another problem, but this time it's much harder. So this problem is also finding pOH slash pH, but this time it's harder because it has a new concept of Ka, which is the value at equilibrium. It is KQ, but specifically for acidic solutions. So Ka, usually for all equilibrium, they just write KEQ, that's the value. But for acids, it is Ka. So now let's read the problem. A 3.27 molar perchloric acid solution has a Ka of 1.3 times 10 to the negative 3. Calculate the pOH of the acidic solution at equilibrium. Okay, so first off, we have to figure out how we're going to go about this. So we want to find the pOH. So we know the formula for pOH is pOH equals a negative log of the OH concentration. So now we have to figure out how to figure out the OH concentration. Now it gives us perchloric acid 0.27 moles of perchloric acid, and also gives us a Ka value. Now the Ka slash KQ value is equal to the concentration of the reactants. Products. Concentration of the products. Products is on top, divided by the concentration of the reactants. So we have to write the chemical equation at equilibrium of perchloric acid. Now, for those of you who haven't memorized your polyatomic ions, you need to. Perchloric acid is HClO4, and ClO4 is perchlorate. So let's write it. HClO4. Now, HCl4 combines is at equilibrium with H plus, because you see there is an H right here, so it's H plus what's left over. What does it disassociate to? ClO4, and if you know the polyatomic ion, it's a minus, and also you don't need to know that, but whatever. So you have this, and you now have the products, products, yeah, H plus and ClO4, those will go up here, and then you have the reactant. So you actually only need one of these in this example. So then you can create a rice chart to find out these values. So let's make a rice chart. R-I-C-E, or ice chart. I like to call it both, rice and ice. You don't really need the R, but it stands for reaction, so the reaction up here. And then I stands for initial values, which we'll use this, 3.27. C stands for change. How does it change in the reaction of equilibrium? And then E stands for at equilibrium. So the reaction is HClO4 is at equilibrium with H plus, which is actually what we want to find, and ClO4. Now, let me explain why we need to find H plus, because we want to find the pOH of this solution. So one way you can find the pOH is if we have the concentration of OH, which we can find if we first find the concentration of H plus. So let's find the concentration of H plus using this rice chart. So let's create our chart. Okay, our three things. So the initial value for this, as we know, is 3.27 molar. Actually, we don't need to write the M. This is all in molars. 3.27 molar. This is nothing. It doesn't start at anything. Now, note that HClO4 is a strong acid. You need to memorize all the strong acids. So, it disassociates easily. But in this problem, it gives us the Ka, which means that it doesn't dissociate completely, and that it won't dissociate completely. It will only dissociate partly, but it will dissociate a lot because it's a strong acid. So minus X is the amount that it dissociates, and this gets plus X, this gets a plus X, and this ends up as X, This equation is balanced, by the way. You need to remember to always balance your equation. And then this is 3.27 minus x. So you have your values. So now let's find the concentrations. So we have what Ka equals to. So let's write our formula. What was it? 1.3 times 10 raised to the minus 3 equals the products, so x times x squared over the reactants, 3.27 minus x. Now, in this equation, first we would multiply the bottom portion, this portion, to both sides, and then we would do stuff and create a quadratic equation. But honestly, I do not want to deal with quadratic equations, especially with numbers as small as this, and all chemists don't. So there's something we can do, which is use our math logic. Now, this number is really, really small. It's 10 to the minus 3, so it's around 0.000 something. It's pretty small. And if this is a small number, if this here is a small number, that means that this side, this needs to be, if this is a small number, that means that this side needs to be a small number as well. Now, what makes this side a small number? Well, if x squared is large, then this is not going to be a small number, because let's say x squared is, x is 2, that's 4 over around 1, that's going to be 4. And if x squared is, x is 3, that's going to be 9 around 0, or around 0.27, that's going to be a really large number, 9 divided by 0.27. So that means x has to be a relatively small number. Now, how small does x have to be? So, a really small number on the numerator divided by a really large number, or relatively large, like 3.27 on the denominator, will render a really small thing here. Like, for example, 0.01 divided by 3.27, we'll get something like around here. I'd estimate like 0.0 something. That's what I'd say. So that means that x has to be extremely small. Now, what can we do with that information? We can say that this x right here, we're assuming it's so small that it's around 0. Like, what we're saying is that this x right here in the denominator is so close to 0 that in comparison to the 3.27, it won't make a big difference. And we're assuming that it's so small that it will just be a 3.27 over x squared. No, x squared over 3.27. Whereas in comparison to 3.27, we're assuming that it is not large enough to make a difference, and then we're getting this only. Now, whether this is an accurate assumption, a valid assumption, we'll come to later. But first, let's solve it for. So we gotta solve for x using the equation x squared over 3.275 equals 1.3 times 10 to the negative 3. So instead of doing this bad, ugly equation, so 1.3 times 10 raised to the negative 3 equals x squared over 3.27. Multiply both sides with 3.27, and we get 3.27. Multiply both sides by that, you get 4.2. 4.251 times 10 to the negative 3 equals x squared. Now, take the square root of that, you get x equals 0.651. That's what x is equal to, 0.0651. Now, what you gotta do is plug this into your rice chart. So you have x, so x here is also, and this x here is equal to 0 0.0651 and 0.0651, and this is equal to 3.27 minus 0.0651. Now you have your hydronium concentration at equilibrium, which is 0.0651. Now before we move on to find the pOH, I want to talk about the 5% rule. Now in this step, we got rid of this small x here and just made it like this, because the x was too minimal. Now in most of the scenarios you will encounter, the x will be so minimal that this will be true, but sometimes it won't be. And to find out whether our assumption this was too small was correct, you have to use something called the 5% rule. And what that says is that to find 5% rule says to find whether it was valid, you have to take your found x, whatever you found for x, divided by the starting concentration of the reactants, which is 3.27, x slash 3.27, and if this is less than 5% or 0.05, then it is a valid assumption. So if you plug in 0.065 divided by 3.27, you will get, let me plug this in on my calculator, 0.065 divided by 0.27. You have 0.065 divided by 3.27. It is less than 5%, so you are good to go. Check. Well, I forgot the exact value. Check. Anyway, so it is a valid assumption. So now you have your hydronium concentration of 0.0651. So you can write this. I will use brown. H plus concentration equals 0.0651. Now, are we done? No, we're not done. It asks us to find the pOH of the acid solution at equilibrium. So, this H plus is suited to find pH, not pOH. So what we can do is find the pH and then take 14 minus that to find the pOH. So the pH is equal to the negative log of this H plus concentration. H plus concentration. Now, if you plug this into your calculator, you'll get, let me plug it into the calculator, negative, sorry, log is log. Log is 10. So, no, here's how the calculator works. So, 0.065 log base 10 times negative 1 times 1, just 1, and I actually just pretend the 1 doesn't exist. You get 1.1870 as the pH. So that's around 1.19. So you get pH equals 1.19. But you want to find the pOH. So what you can do is you can do 14 minus this. So 14 minus 1.19, you should get 12.81 pOH. And this tells you that this is an acidic solution and it's acidic, so it checks. So our final answer is 12.81. Okay, that took some time, but once you get used to these types of problems, you can do it much faster than what just went down. So now the next problem is a student prepared a 1.0 molar solution of Hyont acid. The student found, that was typo, the student found the pH of the solution to be 2.0. Calculate the Ka value for the acid solution. Okay, find the Ka value for the acid solution. So let's just write down our formula. Ka equals the products over the reactants. So it says of high-ion acid. Now don't be afraid if you see high-ion and you're like, what the heck is this? High-ion acid is something that was just made up in this problem. It's just meant to make, just like to confuse students. But you can just write it as JHJ. And this is not a real compound. This is just for explanation purposes. So you have an HA compound, and it's at equilibrium, and it goes to H plus, there's the H there, and then J minus. Now remember, this is not an actual compound, but it does not matter what type of compound it is in this problem. So you have this. Now let's set up our rice chart. R-I-C-E. I'll use the equation straight. Okay, so it starts out with 1 molar of that. So 1, just pretend it's there. Wait, no, I'll write this here. 1 molar, and 0 of these. And the student found pH to be that. So it's the same as this problem, except we got to work backwards. So let's find the hydronium concentration, because we know that pH is 2.0 equals negative log the H plus concentration. So we can multiply both sides by 2, negative 1, we get negative 2, so then this is an imaginary base 10 here, 10 raised to the negative 2 equals H plus equals, you guys know what 10 raised to negative 2 is, that's 0.001, 0.01, sorry. That's what it equals to. So you know that is a plus x, which is 0.01. 0.01 is the final thing here. Now, because of this equation, there's a 1 here, there's a 1 here, there's a 1 here. This is also going to be plus the same thing, 0.01. Because of stoichiometry, you can say that that's true. And this is also going to be minus that, 0.01. And if you do this, you'll get 0.99. Now you just got to find the Ka value, plug this stuff in. I'll plug it in up here. So 0.01. The coefficient is 1 because it's just hydrogen, 1 hydrogen, just imaginary 1. And then multiplied by another 0.01. Reach to 1, and then over 0.09. 0.99, sorry, 0.99. From here, we can go here and say 0.01 squared over 0.99. Oops, wrong 99. That equals 1.1 times 1.01 times 10 to the negative 4. Don't leave your answer in some crazy lot of zeros decimal. Just put it in scientific notation. That's easier for everyone. But notice that this is a 2 significant figures problem. So you can just take off this 1 and get the right number of significant figures. But if it doesn't ask for sig figs, then you can just leave it as whatever you want. So make sure you put in scientific notation, because usually that's a safer move, especially since it's a lot more cleaner. So that's the answer. Now in this video, I hope you learned a lot of stuff about these problems using rice charts, doing logs. These problems were pretty difficult, but with a lot of practice, it should become easy. Bye.